In quantum mechanics, the motion of a particle is best described by probability waves. So we have the Schrödinger equation, and the solution of the Schrödinger equation gives us a wave function. If we do the mod square of the wave function, it essentially gives us an idea about the probability density of a particle being found in a given region. So if the amplitude of this wave function solution is high in a certain region, it simply means that the likelihood of the particle being found in that region is greater compared to another region in which the amplitude of that wave function is less. So essentially, it is this probability density, which is the wave function mod square, that gives us an idea about the likelihood of a particle being found in a given region. Now, what if the particle is in motion? If a particle is moving from one region to another, then how does that change this probability density? You guessed it right. The probability density also changes. You see, initially the particle was here, so the amplitude of the probability density was high here. But after some time, when the particle goes to another region, the amplitude of that wave function and the corresponding probability density will be greater in that region. So essentially, if you think of this probability density as some kind of a fluid, then the movement of the particle from one region to another will also correspond to some kind of a fluid motion, where the amount of probability density from this region will seep into the nearby region where the particle has penetrated. So what I'm trying to say is, if we think of the probability density of the particle in quantum mechanics as a fluid, then probability current is essentially the rate of the flow of this fluid. That's what probability current is. But because the total amount of probability of a particle being found in the entire universe always remains equal to 1, so if I want to find out the probability of a particle from minus infinity to plus infinity, it is always equal to 1. Therefore, there is a continuity equation which is also associated with this kind of a probability current, because if there is a decrease in the probability density associated with the particle in one region, there is going to be an increase in the probability density in the nearby regions, so that the overall integral remains equal. So there is a conservation of probability that happens as a particle goes from point 1 to point B, and it happens in such a manner that there is a current that is associated with the evolution of this probability wave. So in this video, I want to derive that probability current. I want to derive the equation of continuity, and I will give you a couple of examples of how we can calculate the probability current, for example, for free particles, for particle in infinite potential well, and also for the cases of step potentials, how we calculate reflection and transmission coefficients. So let's start. So we will start with the time dependent Schrödinger equation in 3D. Alright. So in 3D, the time dependent Schrödinger equation is simply iota h cut del psi upon del t is equal to minus h cross square upon 2m del square. Here del square is a Laplacian, psi plus v psi. Couple of things, if you are familiar with the Schrödinger equation, then the symbols probably make sense to you. Here psi is nothing but the wave function solution, and depending upon whether we are studying the system in 1D, 2D or 3D, it could be a function of x or r. So in this case, we are going to be studying for 3D, so it's going to be a function of r and of course time. Here del square is the Laplacian, because I am writing the Schrödinger equation in 3 dimensions. So the Laplacian will simply be the partial derivatives with respect to x to the second order. Similarly for the y, del 2 upon del y2 plus del 2 upon del z2. Alright, so if I had just the Schrödinger equation in 1D, I will just have only one of those components, but because I am writing this in 3D, I have all the 3 combined together in the Laplacian operator. Okay, now I want to write its complex conjugate. So you understand what complex conjugate means? So essentially, because this equation involves imaginary terms, I am simply going to substitute the iota, the imaginary number, with minus iota. And then I end up getting minus iota h cut del psi star, because the wave function in the context of quantum mechanics can also be complex. So this simply represents that it is a complex conjugate of that particular wave function, is equal to minus h cross square upon 2m del square psi star plus v psi star. Usually the potentials are very much real. Now I'm going to multiply the first equation with psi star on each side. Then I end up getting iota h cut psi star del psi upon del t is equal to minus h cut square upon 2m psi star del 2 psi plus v. This is just a multiplication between v and psi, so I can write v psi star psi. And in the second equation, the complex conjugate version of the Schrodinger equation, I am simply going to multiply psi on the right hand side. So here I will end up getting minus iota h cut del psi star upon del x psi is equal to minus h cut square upon 2m del square psi star psi plus v psi star psi. So what I'm trying to do is I'm essentially trying to obtain the equation of continuity, because from there we can easily find out the probability current. We will get a derivation of the probability current. So this is what I did to both the time dependent Schrodinger equation, the original version and its complex conjugate version, and then let's say I call it point number 1 and I call this point number 2. Now I'm going to subtract point number 2 from point number 1. So subtract 2 from 1. Alright, so if I do that, it simply becomes iota h cut psi star del psi upon del t minus plus iota h cut del psi star upon del x. Oh, sorry, this should be del t, right? Yeah, I have this habit of making silly just errors, so this should be t here, but I always end up rectifying them later on. So this is t and then psi here. This ends up becoming this first equation minus h cross square upon 2m psi star del 2 psi plus v psi star psi minus again plus, we have h cross square upon 2m del 2 psi star psi, and then we have minus v psi star psi. So here v psi star psi, this is just a multiplicative term between all these three terms. So, and this is plus and this is minus, so these two terms gets cancelled, and all that we are left is the remaining options. So let me just rub the other side of the board so that I can continue with the calculations. Now if you look at the left hand side, we have these two terms. They can together be written in a very combined manner. So I can write it in this particular way. So this simply would become iota h cross del upon del t of, you have psi star psi. So if I expand this, I end up getting these two terms, right? Psi star del psi upon del t plus psi del psi star upon del t psi. And in the right hand side, these two terms gets cancelled, and remaining I have this positive term and negative term. If I combine them together, this simply becomes h cross square upon 2m, and within brackets we have del 2 psi star multiplied by psi minus, you have psi star del 2 psi. Now I want to simplify this. To simplify this, let us look at a couple of separate calculations. So let's just keep this equation here for a moment, okay? And let us just look at these expressions. So if I take del, I just take del, okay? Here del is just, it's not a Laplacian operator, it's just del. as a vector quantity, and I operate it on psi star del psi. So the reason I'm writing all of these is just to simplify the expression above, that's all. So essentially this becomes psi star, and then you have del square, the Laplacian psi, one term, and the next term is del psi star, and then del psi. Okay, fine. Now I want to look at one more expression. Let's say this is del psi and then del psi star. Okay, so if I look at this particular expression, this simply becomes psi del square psi star plus del psi star. So there you have it. This particular expression on the right hand side of this is nothing but what we had initially here in the right hand side. Okay, so I can substitute this particular expression here, and then I will have a different look to the equation, which is going to help us reach our final sort of result. So if I write down this particular equation again, the left hand side is iota h cross del upon del t of, now here what is psi star psi? You are familiar with the fact that psi star psi is nothing but probability density of the particle being found, let's suppose, around a given location. So let me just write it in this manner. Let me just write it as P. So then we have del P upon del T is equal to, here again I have a couple of things to keep in mind. H cross square upon 2m. If I substitute this with this expression, I can take del common, and then I will be left with this particular expression, psi del psi star minus psi star del psi. Keep in mind that this is a vector quantity which I am going to name as probability current. So this quantity that I have here, this quantity I am going to name as probability current. Okay. Why? It will become clear in a moment. So if I rewrite this entire expression, here h cross and this h cross gets cancelled, and if I take iota to the right hand side, 1 upon iota becomes minus iota, then the entire expression I bring it to the left hand side, then I end up getting finally del P upon del T. Now keep in mind that del P upon del T is what? Because P is just probability density, it is simply time derivative of the probability density. It is telling us how the probability density is changing with time as a particle is moving from one location to another. So it has something to do with the motion of a particle and how the probability density changes with time. So this plus I will have iota h cross upon 2m, and then I have here divergence of this particular quantity which I call as probability current J is equal to 0. This equation is known as the differential form of the continuity equation. Alright. This is the differential form of the continuity equation. Okay. Differential form of continuity equation. Now, what is a continuity equation? A continuity equation is essentially a transport equation in physics, because it tells us something about the transport of a quantity like mass or charge or momentum, etc. So a continuity equation has to do with transport of a particular quantity, in this case probability density. I again made a silly typo. We usually include these constants within the definition of the probability current. So the probability current is this term multiplied by this particular term. So I should remove this constant here. Okay, I should remove this constant. So the proper way of writing the continuity equation is this, where now I should specify very clearly what these terms mean. J is essentially equal to iota h cut upon 2m times you have psi del psi star minus psi star del psi. Now, of course, this is the expression for a particle's motion in 3 dimensions. In 1 dimension, instead of del, we will just have del upon del x. Alright. So now I was talking about the continuity equation. The continuity equation simply gives us an idea about the transport of some quantity like charge or mass or momenta, and we see these kinds of continuity equations in other branches of physics like electromagnetism or fluid mechanics. So for example, in electromagnetism, we have a continuity equation associated with the flow of charge. So if let's suppose you have an enclosed volume and there is a charge density within that volume and charges are coming out of the volume, then the motion of charges is associated with a current, right? So when charges are coming out of that particular volume, there is a surface current which is J in this particular case, and a continuity equation of the time rate of change of the charge density within the volume, which is associated with the divergence of that particular surface current. So essentially, the time rate of decrease of the charge as charges come out of a differential volume is equal to the net outward flow of the current through that closed surface of that particular volume. We also have continuity equation in fluid dynamics, which has to do with conservation of mass. The earlier has to do with conservation of charge. This has to do with conservation of mass. So whenever a certain kind of a fluid is in motion and we have some sort of a volume, then we have this particular continuity equation that simply gives us an idea about the time derivative of the accumulation or the loss of fluid mass in a given volume, which is related to whether the fluid is flowing in or flowing out, whether that volume is behaving as a sink or a source. Alright, and one consequence of the fluid mechanics continuity equation is that whenever you have fluid flowing through a pipe and you decrease the area of cross section of the pipe, then the velocity of the fluid increases, something that you're probably already familiar with. So by analogy of the charge conservation in electromagnetism and mass conservation in fluid dynamics, we have this kind of a probability conservation in quantum mechanics. So the time rate of change of the probability density even in a given region is associated with the divergence of what is known as probability current. Probability current being the rate of the flow of the probability density, and this is the continuity equation in differential form. I can also show you the continuity equation in integral form. So for that, I'll have to rub this part of the board. So for example, if I rewrite the continuity equation, del P upon del T plus the divergence of the probability current and integrate it with respect to the volume. Okay, so essentially we are dealing with a particular volume which contains the probability density and whether or not the probability density is associated with an outward flow or an inward flow across the surface of that particular volume. So this is equal to 0. So if I write it here, I can separate these terms. I can take the derivative out. Okay, so if I take the derivative out, it simply becomes P dV, right? And then here we have a volumetric integration of del J. Now you are probably familiar with the Gauss divergence theorem. So essentially, if I have a volumetric integration of the divergence of a particular vector field, then that is essentially equal to the surface integration. So over the closed surface enclosing that particular volume of that vector field. So in this case, we have J here, ds. So this is equal to 0 plus time derivative of the probability. Okay, so this is here we have the continuity equation in integral form. So which simply says that the time derivative of the probability of a particular particle enclosed in a given volume is equal to the negative of the surface integration of the current density across that particular surface which encloses the volume in the first place. So this is the continuity equation where J represents a probability current. So essentially J gives you an idea about whether the particle is essentially flowing out of a given volume or going into a given volume. So whether a given volume is acting as a source, whether probability density is actually spreading out of it, the fluid is coming out of it, or it is acting as a sink where the fluid is flowing into it. Alright, so I will give you a couple of examples. So a couple of examples here. First we'll deal with the plane wave solution, okay. For a free particle, we will take its plane wave solution only. Because I just want to simply look at a few cases. Don't want to go too deep into it. So if I take a plane wave solution for a free particle which is going in, let's suppose, 1D. So we had the probability current, right? If you remember, the probability current was given by J is equal to iota h cross upon 2m, and then you have psi del psi star minus psi star del psi, where del here is simply I cap del upon del x plus j cap del upon del y plus k cap del upon del z for 3D. However, most of the time we don't really deal with three-dimensional motion. We restrict our attention to 1D motion. So for 1D motion, so this is for 3D, right? For 1D motion, this would simply look like iota h cross 2m. You have psi del psi star upon del x minus psi star del psi upon del x. So I'm going to use this particular expression here. So if I have a plane wave solution that looks something like, let's suppose, a e to the power I cap kx minus omega t, and you have then the complex conjugate of the plane wave solution, which would look like a e to the power minus iota kx minus omega t. And if I take its derivatives, so if I take del psi upon del x, this is simply going to become iota a k e to the power iota kx minus omega t, and here I have del psi star upon del x would become minus iota a. So because I took psi star, I think I should take a star also, because I don't really know what a is. A could be a complex constant, who knows. So a star k e to the power minus iota kx minus omega t. So if I calculate the probability current for, I should not write vector here, just J, okay, because it's for 1D. So if I calculate the probability current for this plane wave solution, then it becomes iota h cross upon 2m, and here I have psi. So psi is a, I have a e to the power iota kx minus omega t, and then I have d psi star upon dx, which is this quantity. This is nothing but, I should write minus sign here, and iota a star k e to the power minus iota kx minus omega t, first term. Alright, and then we have the second term, which is minus psi star. Psi star is this. You have a star e to the power minus iota kx minus omega t, and then you have d psi upon or del psi upon del x, which is this, which is simply iota a k e to the power iota kx minus omega t. Alright, seems complicated, but it's not really. I mean, if you look at this expression, e to the power iota kx minus omega t and e to the power minus iota kx minus omega t, it gets cancelled here and it gets cancelled here, and all that remains for the probability current for this plane wave solution is iota h cross upon 2m, and here you have iota minus iota a times a star is a mod square k, and minus iota a times a star is a mod square k. So it becomes 2 iota A mod square k, 2 gets cancelled, iota and iota becomes -1, -1 or -1 becomes +1. So this essentially comes out to be A mod square h cross k upon 2m, or 2 gets cancelled, right? 2 terms gets cancelled, I have m here. Now what is h cross k? If you are familiar with the de Broglie hypothesis, then P is essentially equal to h upon lambda. But what is k? K is essentially equal to 2 pi upon lambda. So k is equal to 2 pi upon h times h upon you have lambda. So h upon 2 pi becomes h cross and h upon lambda becomes p. So p upon h cross. So therefore momentum is equal to h cross k. Alright. So h cross k is nothing but the momentum of that moving particle. So I can say p upon m, where p here represents the momentum, okay? And then you have A mod square, but momentum divided by mass is what? For non-relativistic cases, the velocity of the particle A mod square. So for a plane wave solution, which is essentially whenever we deal with particles, when we deal with particles moving in a region where, let's suppose, potential is 0, then for various circumstances we use plane wave solutions. If you look at the probability density of a plane wave solution, the probability density of a plane wave solution essentially comes out to be a constant if you look at it. Because if I calculate psi star psi, which is the probability density in the given region, it comes out to be A mod square. It comes out to be a constant. However, if I calculate the probability current, that is A mod square times V. So because a particle is in motion, the probability current contains some information about whether the particle is in motion or not. Therefore, the probability current doesn't actually come out to be 0. Even though the probability density for a plane wave solution remains constant, the probability current contains the velocity term and of course the amplitude of the wave function mod square term. So this is for a plane wave solution. Let's also look at a couple of other examples. So you must be familiar with the infinite square well potential. We haven't really done that case in a detailed manner in this particular series. But if you are already familiar with the results, I can just show you quickly with a very quick calculation what is going to be the probability current for that kind of a scenario. So if I have an infinite square well potential, which simply means that let's suppose there's a particle whose motion is restricted to the x-axis, but it is also restricted between 0 and A. At 0 and A, you have infinite potential barriers that the particle cannot really penetrate through. So the particle is essentially stuck in this particular region. Now if you're familiar with this particular problem, the eigenfunction solution of this particular problem is very, very simple. If I just write down the eigenfunction solution, it comes out to be root over 2 upon A sine n pi x upon A. If I write down the wave function solution, which means I include the time dependence here. So if I include the time dependence, so there is iota e to the power iota minus iota omega t. So now if I calculate the probability current for this particular scenario, so in that case what do I have to do? First I have to find out psi star. So what is psi star? Psi star is 2 upon A. Let's do this calculation quickly. N pi x upon A e to the power iota becomes plus minus iota, so it's iota omega t. And if I do del psi upon del x, this simply is you have the sine n pi upon A, so root 2 upon A, and then you have n pi upon A, and sine x, derivative of sine x comes out to be cos n pi x upon A, and here e to the power, it's a time function, so therefore it just remains as it is. And then you have d psi star upon del x, so again root 2 upon A, here you have n pi upon A and cos n pi x upon A, and here you have e to the power iota omega t. And then if we calculate the probability current for this particular scenario, then what do we have? Iota h cross upon 2m, and we should have something like this, which is the definition we have. where if I plug in all the values, what should I get? Iota h cut upon 2m. So what is psi? Psi is this. D psi star upon dx is this. So this multiplied by this is 2 upon a and pi upon a sine and pi x upon a cos and pi x upon a. The exponential e to the power iota omega t and e to the minus iota omega t gets cancelled. Alright, and then you have the next psi star times del psi upon del x. These two multiplication we get 2 upon a and pi upon a. Again sine times cos, sine and pi x upon a cos and pi x upon a. And again e to the power minus iota omega t gets cancelled with e to the power iota omega t. So what is this? This is the same as this, right? 2 upon a and pi upon a, sine and pi x upon a, cos and pi x upon a. So these two gets cancelled. So this minus this comes out to be 0. So this is nothing but 0. So the probability current for a particle which is stuck in an infinite square well potential is essentially 0, which means the particle is always confined there, which is what the system actually is. Particle is confined in that region, therefore the probability current actually comes out to be 0. There is no flow of a particle away from that particular region. Now another scenario in which the probability current concept may be useful is in the concept of step potential or any kind of a potential barrier. Okay. Again, I will discuss these topics in detail later on, but because we are dealing with probability current, I am just referring to them in the context of probability current here. Okay. So probability, or rather I should say potential barrier. Potential barrier. So what happens if I have some kind of a potential barrier? Something that looks like this. So like I'll take a very simple step potential example. Okay. So I have a step potential where the V is equal to 0 and there's a particle which is in motion, but then it encounters some kind of a potential barrier. And in that kind of a scenario, the solution that we actually end up having, if you are familiar with it, is something that looks like this. We have this plane wave solution going in the forward direction, a e to the power iota kx minus omega t, but then there is also possibility of reflection of that wave. You see, this is a plane wave, and once a plane wave approaches a barrier and it hits a barrier, there is a possibility of reflection. So then there is another term b e to the power minus iota kx minus omega t, which simply means the waves moving in the backward direction. So you can have a wave traveling forward, which is the incident wave, and you have a wave traveling backward, which is the reflected wave. So this is the incident plane wave corresponding to the particles hitting the barrier, and this is the reflected wave corresponding to the particles which come reflected backwards. Now in the context of probability current, what I wanted to mention here is quite simple. The probability of reflection or the probability of transmission can be calculated using the concept of probability current. Because the probability current essentially refers to the rate of the flow of the probability density associated with the motion of a particle, right? So if a particle reflects backwards, then the probability current ratio between the incident and the reflected wave essentially gives us an idea about what is the probability that the particle will get reflected as opposed to being transmitted. So for example, the reflection coefficient or the probability of reflection is simply equal to the probability current associated with the reflected wave. What is the reflected wave? This is the reflected wave, and upon the incident wave. Which is the incident wave? This is the incident wave. Now I already calculated for the incident wave the probability current, which came out to be something like this. You remember? H cut k upon m a mod square. So if I do the same for this particular reflected wave and I plug those values in, I essentially end up getting a upon b. So a upon b mod square. This is what I actually end up getting for this kind of a scenario. And if I, let's suppose, calculate the case for transmission coefficient Transmission coefficient will essentially be the probability current associated with the transmitted wave upon probability current associated with the incident wave. Now there I will have probably some other, so I'll have to rewrite the transmitted wave as another plane wave solution, but I'll just keep it here for the time being, okay? And it just so happens that whatever reflection and transmission takes place, it always ends up giving us an addition equal to 1, okay? So probability current concept is useful, especially if we are dealing with plane waves hitting some kind of a potential barrier and we are interested in figuring out the probability of reflection or transmission. Then the probability current ratios will basically give us an idea about whether what is the percentage of reflection or transmission for that particular system if certain particles are incident on it. Alright, so therefore the probability current is kind of like a useful concept that you will see being applied in different kinds of problems, especially when dealing with various kinds of potentials, giving us some kind of an idea about the time evolution of probability density of a given system, right? So if a particle in a quantum mechanical world is best described by probability wave, and these probability waves are flowing, just like the fluid motion, and they are sort of flowing, trying to give us an idea about the movement of the particle, then probability current, which is the rate of flow of this kind of a probability density, gives us an idea about whether the particle is moving in a certain direction, going into a volume, out of the volume. Just gives us a general idea about the time evolution of that probability density. So that is all for today's video. Thank you so much. Take care. Bye bye.